We'll now turn our attention to an introduction to GPU computing, and we're going to look in particular at the use of the CUDA platform, which is Nvidia's development environment for what they call their Compute Unified Device Architecture. So by way of an introduction here, I want to compare the notion of a CPU, the core that's running the main part of your computer, from a GPU, the graphics processing unit. So a CPU tends to be a very complex device. The individual cores that are on the main processing unit of your laptop or desktop are very sophisticated general purpose computing engines that know how to do all sorts of things in order to support a fairly complex mix of arbitrarily complex kind of computations. So there's caches, and there's instruction scheduling, and there's out-of-order execution, and there's all of the other pieces and parts, memory management, and so forth, that are there on the CPU. Now, that's great from the standpoint of power and flexibility, right? These kinds of CPU chips can run your operating system. They can run all the different applications that you use and do all of those things fairly well, fairly efficiently, fairly performantly. And that's a positive thing. One of the downsides, though, of this complexity is that it restricts the number of cores that we can physically get on a chip. And you're familiar with the notion of the power wall and the fact that as processors have gotten more complex and more power hungry, that the amount of processor cores that we can physically put on a chip before we run into thermal problems is relatively restrictive. So a current generation of chips that are going into laptops and desktops are going to typically have, say, 4 to 8 cores on the processor itself. And that's about all we can get at the clock speeds that we want to run them at. So very important. Obviously, the core element of any computer system is going to be that CPU, but it has some limitations in terms of how well it scales to larger and larger number of cores. The GPU, on the other hand, uses much simpler cores. Therefore, they have fewer transistors. Therefore, they consume less power. Therefore, you can put more of them on a chip before you start running into thermal processing problems, and you can still clock them fairly quickly. So there's essentially on a GPU, we end up with more hardware, more of the transistors that are on that chip. There's more of them that are focused on computation proper, as opposed to all these other supporting functions that a CPU provides. The upshot of that is that we have more power efficiency. For the same number of watts of power that's generated by that chip, we can do more pure computation than we can do when we're thinking about a CPU, which has many fewer cores. Now, of course, there's no free lunch. So with the GPU, we have a more restricted programming model. All that the GPU knows how to do, basically, is read in data, write out data, and do arithmetic computations. That's really kind of its forte. And because it's simplified from the complexity of a full-on CPU, we can get more cores on the chip. So in the aggregate, the amount of computing capacity per square millimeter on the chip of a GPU is going to vastly outstrip the amount of power per square millimeter on a CPU. Because of this difference in terms of the basic capabilities of the different kinds of processors that we'll be dealing with now, we want to also have a little bit of a different focus on how we measure performance. When we're thinking about CPU performance, we're most often going to talk about latency, which is a measure of the total amount of time it takes to do one thing, to do one computation, to complete the rendering of one video, to render one frame of a video game or something like that. So we want to try to minimize the time of individual tasks, and we're going to measure latency in a time unit, seconds, milliseconds, microseconds, nanoseconds, whatever. And again, that's going to be really appropriate for measuring the performance of CPU behavior. On the other hand, when we're thinking about GPUs, again, we have a less capable processor, but we've got a bunch of them. And so a better approach for measuring the performance of a processing environment like that is going to be to use a different metric that we call throughput. So instead of talking about the absolute time it takes to complete some task, what we're talking about with throughput is the number of times we can do something per unit time. So we want to maximize what I've said here as just stuff per time. right? The number of jobs we can run per hour, or maybe in the context of graphics, the number of pixels that we can render per second. And that's going to be the focus of the GPU. So again, latency is a time, and on CPUs, we're often going to want to make that time as small as we can. Throughput is operations per time, and that's going to be a more appropriate metric for a GPU, where we can throw a lot of processing elements at the problem, but they're less capable on their own. But together, they yield very, very high performance in terms of the amount of data that we can get through per unit time. What we're introducing here is a heterogeneous model for programming. Up to this point, even in this class where we've been dealing with a bunch of CPU cores as opposed to a single core, which is what you've encountered in most classes, here we've now got sort of two very different kinds of processors, which is what I've been talking about so far. We've got the CPU, the complex instruction set architecture that runs the whole show, and we've got the GPU that's a bunch of smaller, simpler processors that are kind of more focused on doing math. In this setting, we need to be able to deal with both of those types of processors, hence heterogeneous programming. Some terminology here. The CPU is usually referred to as the host. So it's, again, kind of running the show. It's at the center of the behavior of this program. And then the GPU is referred to as the device. It sounds very generic, but that's usually the terminology that's used here. So the host is going to run what you might think of as sort of a normal program, right? It's going to start up from the operating system. It's going to begin execution. And what it's going to do is enlist the help of the GPU, the device, in order to be able to solve the particular problem or to carry out that computation. There's going to be different code that's going to run on the CPU versus what's going to be running on the GPU. And the GPU code is usually called a kernel. And this is kind of lost in the mists of time why we call it that, but it's basically kind of a core piece of computation that's at the core of what we're trying to compute, and we refer to it as the kernel. So one of the jobs, as we'll see, of the host code is to start things going and then communicate with the GPU in such a way that it can kind of deliver the code that needs to be executed on the GPU to the GPUs, and also provide access to the data that the GPUs are going to compute. And just some terminology here, when we talk about this heterogeneous programming model, we talk about how the host is going to launch kernels, the code, on the device, the GPU. Now, with respect to the specific architecture we're talking about here, the Nvidia Architecture and their CUDA platform, what we'll see when we're writing programs for this is that we're going to write one program that's going to provide functionality for both the CPU and the GPU. So although we'll execute a single program, what we'll see is that one part of that code is going to run on the CPU, kind of, again, this central core that's coordinating the execution. And part of that code is going to be delivered to the GPU, to the device, and it's going to execute there. So we'll code both sides of that in one program, but at runtime, the execution environment is going to arrange for the appropriate code to be delivered to the GPU to run there. And the same compiler, as we'll see, is going to generate the code for both of those architectures. And obviously, because the CPU is one type of processor and the GPU is a different type of processor, that same compiler is actually going to generate code that's targeting two different instruction set architectures, which is a little unusual. We also need to be able to think about memory. So when we're thinking about just programming on a CPU, even if we're doing it in parallel using pthreads or MPI or something like that, we're really only worried about kind of one memory in the sense of the total storage available to store our program and our data. In the case of the NVIDIA context, we have a separate memory for the CPU, the one that's on the motherboard as we're used to, but then the GPU itself, which oftentimes is going to be something that's plugged into a bus slot on a separate card, has its own memory. So if you look at a spec for a GPU or a graphics board, it'll tell you what kind of GPU is on the board and how much video memory it has, and that's basically what we're talking about. We've got separate memory on that board that's accessible to the GPU in the same way that the memory on the motherboard is accessible to the CPU. We'll see, though, as I've been mentioning, that the CPU is kind of in charge of managing memory. So, for example, a very typical partitioning of the functionality of the program that we're going to run is going to have the CPU start out, and what it's going to do is it's going to allocate storage that it needs on the main memory on the PC, but it'll also allocate memory on the graphics card. It also has the capability of moving data from CPU memory to GPU memory. And after the CPU has asked the GPU to complete the computation, it can move data back from the GPU memory to the CPU memory. So again, the CPU remains in charge, as I've said here, in the sense that it allocates storage both for it and for the GPU, and it moves data back and forth between it and the GPU. So in a typical program running on CUDA, as I've just kind of suggested, the first step once the CPU starts running is going to be to allocate memory for the GPU. And we'll see that in the CUDA environment, we've got these function calls that look sort of like our conventional idea about dynamic memory allocation, but they've got this CUDA prefix that marks them out as things that are working specifically on the CUDA memory. So we'd still have malloc available to us in the CPU side of the program, but when we want to allocate memory on the graphics card, or the memory that's used by the GPU, we're going to use a very similar looking function called CUDA malloc. So after we've allocated space on the graphics board for the GPU, the next thing we need to be able to do is fill that up with the memory that's going to, or with the data that's going to be used as the input to the program that's going to run on the GPU. So normally we're going to either, we'll create that on the CPU side, or we'll load it off of disk or grab it off the network and store it into CPU memory, and then the CPU will copy that data over to the GPU, and that's going to use another conventional sounding C-style, Unix-style function called memcopy, except this is the CUDA memcopy version of that can move information from CPU memory to GPU memory and vice versa. So the second step is basically setting up the GPU to prepare to do the calculation by putting the data on the memory that the GPU has direct access to. Then the CPU is going to launch that kernel. Remember, the kernel is the code that's running on the GPU itself. Basically tell the GPU to go ahead and process the data that it has loaded into GPU memory. And this is really where the fast part happens, right? This is where the parallelism comes in. The GPU can go to work on those data with all the cores it has available to it. And then when that's done, the CPU can move the data or the results back from GPU memory to CPU memory, where it might, again, store it to disk, send it across the network, or whatever. So that's a very, very typical pattern. Allocate GPU memory, put the problem data in that GPU memory, fire off the GPU to do its thing, and then copy results back from GPU memory to the CPU. You'll notice that there's some things that are quite common across all of these different paradigms for parallel computing, and one of them is that we still have this kind of a trade-off between, in this case, again, computation and communication. It takes a non-trivial amount of time to move information from CPU memory to GPU memory and vice versa. And although that's not really communication in the sense of moving things across the network like we have with MPI, we still have that delay, that source of overhead that is going to reduce our efficiency if the overhead due to copying between memories begins to eclipse the amount of time that we're actually spending doing useful computation in parallel on the GPU. Some other comments: we can launch lots of threads really efficiently, right? So threads in the thousands is not at all unusual on the GPU. So again, we've got lots of small processors, but they're small but mighty. We can run a lot of those threads in parallel. So that's really the source of the performance improvement that we get from using a GPU for parallel processing. Let's think about the programming paradigm we want to have in mind when we're thinking about how to program a GPU. This is kind of the big idea. The kernel, that piece of code that's going to run on the GPU itself, is set up in such a way that it looks like it's just a serial program. It's just a simple computation. And in fact, if you look at the code itself, it doesn't really say anything at all about parallelism. When we did pthreads programming, right, we had to do pthread create, we had to do sends and receives and all that sort of thing. pthread join at the end. With MPI, we had to create a separate function that was going to run on the individual processors throughout the multicomputer. It was very explicit in a sense that we're going to do things in a different way than we normally do in a sequential program. The idea behind the kernel is that it doesn't really have anything explicit about it in terms of parallelism. It's just going to be a generally relatively small, simple program or simple function even that's going to execute on the GPUs. The parallelism comes into play because the runtime environment can launch that kernel on many, many different processors in the GPU. So we can write the code as if it's just going to run in one thread on the GPU, but it's actually going to run on a whole bunch of threads, and it's up to the CPU and the runtime environment to sort of configure what that's going to look like when we begin execution. So the CPU might run that single kernel on hundreds or thousands or even millions of threads simultaneously across the multicomputer. The only nod that the individual pieces of code have to the fact that they're running in multiple places simultaneously is what's known as a thread index, so that the individual functions, the kernels that are running on different GPU processors, can figure out which portion of the computation they're supposed to be able to do. So this is kind of the moral equivalent of the thread ID in pthreads or the rank in MPI. The thread index will be available to us in the GPU code. Let's take a look at a small example of a CUDA program. One thing to notice here is that the file extension on this program is .cu instead of .c. It's still a C program, but that's the convention for CUDA programs. And otherwise, it looks a lot like sort of normal C so far. What this program is going to do is take an array of floating point values, and it's going to square each of the elements in that array, just multiply it by itself. Super simple problem to illustrate the process of getting the GPU involved. I've got a couple of constants that I'm defining in here. The first is array size, which is just the number of elements in that array. And then the number of bytes that are going to be used by that array is going to be the size, the number of elements, times the size of each element, which is just size of float. So I've set those up to be used later. Next thing I'm going to do is I'm going to establish the data that I'm going to store on the CPU side in CPU memory. And one of the conventions, you don't have to observe this, but I find it helpful myself, is that when I'm declaring a variable that's going to be allocated in host memory, I'm going to prefix it with an H. So H in is, in this case, it's an array of floats that has array size elements, 64 in this case, and that's going to be memory allocated in normal CPU storage. So I've called it H and in for the input. And that's going to be the original array. And then I'm going to have another one called H out that's the same size, and that's where I'm going to store the values that the GPU calculates after I move them back to host memory. And then I'm going to initialize the input array by just giving it values from 0 to 1 less than the array size, and I've just cast those into floats in the input array. So just simple, it's going to have 0, 1, 2, 3, 4, and so forth. All right, plain vanilla stuff so far. Now, I also need to be able to allocate storage on the GPU. The GPU itself is, it's this device. It's kind of passive in a way. It's waiting for the host processor, for the CPU, to tell it how to get set up before it starts doing its calculation. So what I've done here is declared two additional floating point pointers. Right, it's a float star called D in, and the D stands for device. So H underscore something is a host variable, D underscore something is a device variable. That's not something that the compiler pays attention to. It's just a convention for the programmer. Okay, so don't expect it to magically allocate things one side or the other, depending on how you declare it. What we want to do is allocate memory on the GPU. And as I mentioned before, the function that we're going to use for that is called CUDA malloc. So malloc is the memory allocation primitive for allocating dynamic storage, and it's named similarly here in the CUDA environment to the way that it's used in the standard C library. One of the arguments that gets passed to malloc is the number of bytes to allocate. And that's this array bytes value that I calculated up here as the size of the array times the size of the elements of the array. In addition to that, we don't get a pointer back from CUDA malloc that refers to that memory on the GPU. Instead, we pass the address of a variable that's going to be filled in by CUDA malloc with information that we can use to refer to the memory on the graphics card. Notice that we don't have direct access to that. We have to access the memory on the GPU by using these CUDA function calls, as we'll see. We can't just reference that address because it's in a completely separate memory. It's kind of like how we can't reference a memory on a different processor when we're doing MPI, right? We have to do some communication. In a sense, when we use these CUDA function calls to move information from our CPU memory to our GPU memory and back, we're doing a similar kind of an operation. We don't have direct access to that memory in the sense of just putting an address out on the address bus of the motherboard. We have access to it by merit of making a function call. So what's coming back from CUDA malloc here is not a pointer as such. It's sort of a memory reference that is only meaningful on GPU memory. But we want to be able to refer to that memory later on, right? We want to be able to copy data into GPU memory and get information back from GPU memory. And this is the way we do it. So you can think of this floating point pointer here, D in and D out, as kind of like addresses, but they're addresses of memory that we don't have direct access to. We still need to know what those addresses are, but in a sense, you could think of these as just kind of opaque values that don't have any meaning to our program outside of the use of them in the CUDA function calls. So the calling convention here for both of these CUDA mallocs is that first parameter needs to be an address of a pointer, right? So these guys are pointers, D in and D out, and we're using the ampersand operation to take the address of those pointers. So although these two values, these two variables store addresses, we want to fill those addresses in from inside of the CUDA malloc call. So we have to pass the address of those things because of the way C passes values by reference. And then the cast here, void star star, is just to get the compiler to be happy about how we're invoking CUDA malloc, because that's the way CUDA malloc is declared. Again, it's declared in the most general possible way. It's a pointer to a void star, which is a pointer to an arbitrary pointer. So the same convention is what we saw when we looked at using p-threads. So after all that, to sum up, what we're going to do here when we call CUDA malloc is we're going to allocate this many bytes in the GPU memory someplace, and we're going to get back from CUDA malloc essentially a handle that is going to allow us to refer to that memory later when we want to move data back and forth. All right, now we can move on to doing the computation. Well, actually, we need to move some data across. So this next CUDA function is what allows us to move information back and forth between host memory and device memory, between CPU memory and GPU memory. So we give it two pointers, D in, right? That's going to be the reference that we have on the CPU side to memory that was actually allocated on the GPU, this particular chunk of memory. And we're going to give a second argument of an address on the CPU side. So H in is what we initialized back here in our setup code that contains the matrix of floating point values that we want to square. Then we have to say how many bytes do we want to move from H in over to D in, and we also need to tell CUDA which direction we're going. So CUDA memcopy host to device says go from host memory to device memory. So it's going to go from this host address to this device address and send that many bytes across. Now we're going to do the calculation, and I'm going to come back to this. This is how we launch the kernel. So we'll come back to that in a second, but I want to just kind of finish talking about the way we're dealing with memory. At the end of this function call, the GPU will have done the calculation of the square of all the elements of that matrix or that array. At that point then, the squared version is still stored in GPU memory in this other chunk of memory that we allocated, the D underscore out. There we have a reference to it through D underscore out. So what we want to do is retrieve that information from the GPU back to the CPU so that we can print it or save it to a file or whatever. We're going to again use CUDA memcopy. The first argument is always the destination, and we want to move the information into H out, which was the array that we declared here in the beginning of the program. And we want to get it from D out, which is where the GPU will have left the squared values of that matrix. And it's still going to be array bytes wide, right? The size of a float times the number of floats. And now we're copying in the opposite direction. So previously we were doing host to device. Now we're doing device to host. So it's going to move the data back to CPU memory. Finally, when we do cleanup, we want to release the memory that we had previously allocated in the GPU. So just like we have a CUDA malloc to allocate storage, we also have a CUDA free to free that storage. And again, we're going to pass in these D in and D out pointers, which again are not meaningful addresses on the CPU. They're meaningful addresses on the GPU. And it's only by merit of using these CUDA function calls that those things can be useful to us. So it's going to basically ask the GPU, go ahead and free up the storage you had previously allocated dynamically back here with CUDA malloc and return them to the pool of available storage on the GPU. That's not necessary for us here in this particular program because we allocated our arrays for input and output as local variables, which means they're going to be allocated on the stack, which means when this function returns, it's going to automatically free that space. In this case, it doesn't really matter because that's all we're doing in this program, so it's going to be freed up anyway by the operating system as it harvests the process. But always good to keep those kinds of things in mind, because if you fail to free up a dynamically allocated storage, you're eventually going to run out of memory in a long-running process. Okay, now let's take a look at the code that's going to run on the GPU. And we'll come back to how we fire that up. So here is a little bit of odd syntax, this double underscore, or what some people call dunderscores. That dunderscore global basically says to the compiler, this is code that's going to run on the GPU. Otherwise, it's pretty plain vanilla C. We'll come back and talk about this particular value here in a second, but you can see here that the square function takes a pointer to some output memory, it takes a pointer to some input memory, and what it's going to do, or what you would normally expect it to do, would be to iterate over all of the elements of the input array, square them, and store them in the output array. However, you don't see a loop in here. And again, this is because when we're thinking about the kernel code, which is what this is, we are only thinking about kind of one thread's worth of what's going to happen on the GPU. And the parallelism is going to come by merit of running that same thread on a bunch of different threads on the GPU. So the business end of this really is these two statements. We're going to read a value at index IDX from the input array, and then we're going to square that and store it back in the output array. So these two lines here are going to execute, this is really the important part of the kernel, it's going to do the basic computation. It's going to square a single value from that array. And we're going to arrange for threads to be created, one for every individual element in the array, and they're all going to do that simultaneously. Note again that this is just an ordinary set of C expressions, right? The dn refers to memory on GPU memory, because that's where this is running, offset at index IDX. The dout refers to an array that's allocated in GPU memory, indexed by IDX, and that's where the resulting value is going to get stored. Now the remaining line in here is where we do have some amount of information from the fact that we're going to run this in parallel, kind of leaking into our kernel code. This thread index.x, and we'll unpack more kind of what that means later, is basically just going to be a value from 0 to the number of threads. So it's quite similar to the rank idea in MPI. What we want to do is have an individual thread just worry about that particular element of the array that we're multiplying. And because every single thread that's going to get fired up is going to have a different thread index.x value from 0 to 63 in this case, each of the threads is going to have its own value for IDX, which means that each thread is going to operate on an independent element within the array, and they're all going to run simultaneously. Okay, so that's the source of the parallelism. Now the remaining piece then is, how do we start this up? Well, there's this weird syntax. There's actually 3 less thans here, and the way that the formatting is working here on this slide, it looks a little bit goofy. But there's 3 ordinary less than characters there. And that's the syntax that we use in CUDA C to tell the program to launch a kernel on the device. The particular function that we want to launch is the square function, right? And that's the one that we declared here. It's called square. And we want to spin it up on array size threads. We'll come back and talk later about the full syntax here in this 1, array size. But when I said before that we're going to have one of those square functions running on each of 64 threads, this is where that's coming from. I know I've got 64 elements in the array. I've got essentially an unlimited number of processors at this scale. So I just allocate 1 thread per element of the array and have it go to town and have them all run simultaneously. And I've got to pass in the output array location and the input array location, which are going to be made available in the kernel code here as dout and dn. And I'm ordering these again in such a way that it looks like dout is going to get the value from din, which is why I'm ordering them that way. So when the program is executing, this is going to start the square function on all of the GPU threads that are involved in this calculation. So again, just to review quickly to the overall structure of these programs, we're going to almost always follow this kind of a pattern. Allocate some storage on the host memory that contains the data we want to calculate. Allocate space on the device memory that will allow us to move the data over there so the GPU can access it. Then move the data over, then do the calculation, then move the results back to host memory where we can store them on disk or send them over the network or whatever, and then make sure that we clean everything up on the device side. And if we had allocated arrays using malloc, for example, here on the host code, we would have also had a cleanup section to free that memory back up. And then the remaining piece is just writing the kernels, which is just a separate function that has this funny global underscore thing to tell the compiler, hey, this is code that's going to run on the device. Finally, just a few comments about the Nvidia architectures. These guys have been in business since the mid-90s. They used to make a product that was just called GeForce. And these were pretty much dedicated graphics cards. This was kind of pre the general purpose GPU era. And one of the reasons that that the GPU chip manufacturers started thinking about general purpose computations is that computer scientists realized that when they had a GPU, it was great for graphics, right, compared to just doing all the graphics with the CPU. But if they could take a problem that wasn't really a graphics problem and kind of backwards convert it into something that looked like a graphics problem, they could then solve that problem on a GPU and then kind of convert the results of that back to the representation of the problem or the solution to that problem in a more familiar formulation. So there's a bunch of work kind of going on here in the parallel computing community to try to sort of hack GPUs to do general purpose computing. And when the chip manufacturers started to realize that that was a thing, they started to make it more tractable for programmers to do parallel programming development in general using GPUs in a way that didn't require all of that monkeying around to convert things so that it looked like a graphics problem and then back again. And that really kind of came to the fore starting around the mid-2000s with the microarchitecture that Nvidia referred to as the Tesla architecture. And I've just kind of listed here a representation of the different architectures that they've gone through and the years in which those were introduced. The current latest and greatest is the Turing architecture. Nvidia has announced the Ampere architecture at this point, but it hasn't actually been released. And I think these are actually all hyperlinks if you want to, from the slides, if you want to go look at some of the details here. It takes you to the Wikipedia page for each of these architectures, and there's a lot more detail available to you on the Nvidia site. I was excited to see today that the next architecture that they're going to use is going to be codenamed Hopper after Admiral Grace Murray Hopper, who was one of the early pioneers of computing, and she invented COBOL, among other important things. She also was the person responsible for coining the term bug after one of the people in her lab actually discovered a bug, a moth, that was wedged inside of an electromechanical relay that was causing the system to work improperly. And I believe that very bug was pulled out of the computer, and the lab tech put it in his lab notebook and taped it in there, and you can actually go find the actual bug from which the word bug came. I think I want to say it's at the Smithsonian, but I'm not entirely certain about that. So that's pretty cool that they're naming the next architecture after her. This is some other information about some of these architectures in terms of their clock speed. And you can see that the clock speeds are in the neighborhood of 1 to 2 gigahertz, except for some of the cores that they've experimented with it, where there was a lot more cores on the chip. They had to turn the clocks down appropriately to avoid the power wall. And then I wasn't able to find ready information for some of these more recent things, but the last one I could find data for was clocking at 1.2 gigahertz, has 5,000 cores, and it generates a performance of 6,000 gigaflops, which is pretty fast. And that's this DP here means double precision. So the early cores were single precision floating point, then they evolved to double precision floating point, and the speed for double precision is usually slower than for single precision. So if you really need accuracy in a calculation, the speed is going to be slightly less. And the more recent architectures have seen additional speed ups and different tweaks to them that are getting them well into the teraflops region, which is just remarkable. This is an example of some output from the program. I mentioned it up here, the device query program. This is just from a MacBook Pro that I had a few years ago that had an Nvidia chipset. And this is information that I got back from that. So this was a GeForce 750M, and you can get information here like how many cores there are, right? The individual CUDA cores, how fast they're being clocked at, how fast the memory is being clocked at, how much information can move back and forth between memory and the chip in one gulp, and so forth. So this information is readily available through the CUDA development toolkit, so you can get some information about the details of the processor that you're running your programs on. Again, the cool thing about this, what I referred to earlier as the big idea, the cool thing is that no matter which architecture you are running on, no matter if it's a recent CUDA deployment or an older one, whatever number of processors you have available on your GPU, you can pretty much run the same code without having to recode anything. We saw before that you can get information about your thread index, for example, and that actually is a little bit more elaborate than what we saw there. But fundamentally, you don't have to make really difficult changes to your code to get it to work on pretty much any GPU chip you find your code running on, which is really an elegant approach to dealing with what could otherwise be a very, very tricky problem.